Electrical metallic tubing, or EMT, cannot be used as an equipment grounding conductor. The National Electrical Code, specifically Section 250.118, outlines the acceptable methods for equipment grounding and bonding. While metal raceways can sometimes serve as equipment grounding conductors, EMT is typically not one of them. A separate equipment grounding conductor is usually required to ensure a low impedance path for fault current. This is crucial for the proper operation of overcurrent protective devices, such as circuit breakers and fuses, during a ground fault. The purpose of an equipment grounding conductor is to provide a path for fault current to return to the source, allowing the overcurrent device to trip and de-energize the circuit. This helps to prevent electrical shock hazards and minimize damage to equipment. When installing electrical systems using EMT, it is essential to install a separate equipment grounding conductor within the conduit. This conductor should be sized according to the requirements of the National Electrical Code based on the size of the overcurrent protective device. The equipment grounding conductor can be either a bare or insulated conductor, and it should be properly connected to all metal enclosures and equipment. The connection points must be clean and free of corrosion to ensure good electrical connection. There are several types of equipment grounding conductors that can be used, including copper conductors, aluminum conductors, and copper-clad aluminum conductors. The choice of conductor material depends on the specific application and the requirements of the National Electrical Code. When installing an equipment grounding conductor in EMT, it is important to ensure that the conductor is properly supported and protected from damage. The conductor should be run continuously and without splices, unless the splices are made in approved junction boxes or enclosures. The equipment grounding conductor should also be properly identified, typically with green insulation or marking tape. This helps to ensure that the conductor is not mistaken for a neutral or hot conductor. In some cases, it may be permissible to use the metal raceway as a supplementary equipment grounding conductor, in addition to the separate equipment grounding conductor. However, this is only allowed under specific conditions and must meet the requirements of the National Electrical Code. It is important to consult the National Electrical Code and any applicable local codes to ensure that the electrical system is properly grounded and bonded. Improper grounding can create a safety hazard and may result in equipment damage or failure. The National Electrical Code Section 250 provides detailed requirements for grounding and bonding electrical systems. It is important to understand these requirements to ensure the safety and reliability of electrical installations. The equipment grounding conductor is an essential component of a properly grounded electrical system. It provides a low impedance path for fault current, which helps to protect people and equipment from electrical shock hazards. When installing electrical systems using EMT, always install a separate equipment grounding conductor in addition to the conduit itself. Ensure that the conductor is properly sized, installed, and connected to all metal enclosures and equipment. This will help to ensure the safety and reliability of the electrical system. Let's delve deeper into the specifics of equipment grounding conductors and their relationship with EMT. Firstly, we must clarify the difference between grounding and bonding. Grounding refers to connecting an electrical system to the earth, providing a reference point for voltage and helping to stabilize the system. Bonding, on the other hand, involves connecting metallic parts of an electrical system together to create a low impedance path for fault current. The equipment grounding conductor plays a crucial role in the bonding process. It connects the non-current carrying metal parts of equipment and enclosures to the grounding system, ensuring that they are at the same electrical potential. This helps to prevent voltage differences that could create a shock hazard. The NEC in Section 250.118 lists approved methods for equipment grounding. These methods typically involve the use of a separate equipment grounding conductor, such as a copper wire or a green insulated wire. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device in the circuit. Table 250.122 in the NEC provides guidance on the appropriate size of the equipment grounding conductor. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the grounding path is minimized. When using EMT, the equipment grounding conductor is typically run inside the conduit along with the circuit conductors. The conductor must be securely connected to all metal enclosures and equipment using approved connectors and fittings. Proper connections are essential to ensure a low impedance path for fault current. The connections must be clean, tight, and free of corrosion. When making connections to enclosures, it is important to use listed grounding bushings or bonding jumpers to ensure a reliable connection. Grounding bushings provide a large surface area for contact and help to reduce the impedance of the connection. Bonding jumpers are used to connect different sections of metal raceway or to bond metal enclosures together. In some cases, it may be necessary to use supplemental grounding electrodes to improve the grounding system. Grounding electrodes are typically metal rods or plates that are buried in the earth. They provide a direct connection to the earth and help to stabilize the voltage of the electrical system. The NEC provides detailed requirements for the installation of grounding electrodes in section 250.50 through 250.70. When installing grounding electrodes, it is important to ensure that they are located in an area with low soil resistivity. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. Low soil resistivity allows for better grounding performance. The NEC also requires that grounding electrodes be protected from physical damage. This can be accomplished by installing the electrodes in a protected location or by using a protective enclosure. It is important to note that the use of EMT does not eliminate the need for an equipment grounding conductor. While EMT can provide some degree of grounding, it is not considered an acceptable substitute for a dedicated equipment grounding conductor. The primary reason for this is that EMT connections may not always be reliable. Over time, the connections can loosen or corrode, which can increase the impedance of the grounding path. This can compromise the effectiveness of the grounding system and increase the risk of electrical shock. Therefore, it is always recommended to install a separate equipment grounding conductor in addition to EMT to ensure a safe and reliable grounding system. In situations where it is not possible to install an equipment grounding conductor within the EMT, other grounding methods may be considered. However, these methods must be approved by the authority having jurisdiction and must meet the requirements of the NEC. Some alternative grounding methods include the use of a metal water pipe as a grounding electrode or the use of a structural metal frame as a grounding conductor. However, these methods are subject to specific limitations and requirements. It is important to consult the NEC and a qualified electrical professional before using any alternative grounding methods. In summary, EMT is not an acceptable substitute for an equipment grounding conductor. A separate equipment grounding conductor must be installed in addition to the EMT to ensure a safe and reliable grounding system. The equipment grounding conductor must be properly sized, installed, and connected to all metal enclosures and equipment. Failure to comply with these requirements can create a safety hazard and may result in equipment damage or failure. Always consult the NEC and a qualified electrical professional for guidance on grounding and bonding electrical systems. Remember, proper grounding is essential for the safety of people and equipment. Grounding provides a low impedance path for fault current to return to the source. Bonding connects metallic parts of an electrical system together to create a low impedance path for fault current. The equipment grounding conductor connects the non-current carrying metal parts of equipment and enclosures to the grounding system. The NEC provides detailed requirements for grounding and bonding electrical systems in section 250. EMT is not an acceptable substitute for an equipment grounding conductor. A separate equipment grounding conductor must be installed in addition to the EMT. The equipment grounding conductor must be properly sized, installed, and connected to all metal enclosures and equipment. Failure to comply with these requirements can create a safety hazard and may result in equipment damage or failure. Always consult the NEC and a qualified electrical professional for guidance on grounding and bonding electrical systems. Safety is paramount when working with electricity. Understanding and adhering to the NEC guidelines on grounding and bonding is critical for protecting people and property. Remember that electrical codes are constantly evolving, so it is crucial to stay updated on the latest requirements. Regularly review the NEC and consult with experienced professionals to ensure that your electrical installations are safe and compliant. The correct installation of the equipment grounding conductor minimizes the risk of electrical shock by providing a path for fault current that trips the overcurrent protective device. This is why NEC mandates the use of a separate equipment grounding conductor with EMT, as the conduit itself is not considered a reliable grounding path. It is also crucial to perform regular inspections and maintenance on electrical systems to identify and address any potential grounding issues. Loose connections, corroded components, and damaged conductors can all compromise the effectiveness of the grounding system. Promptly address any such issues to maintain the safety and reliability of the electrical installation. Additionally, it is important to use the correct tools and equipment when working with electrical systems. Using improper tools or equipment can damage conductors, create loose connections, and increase the risk of electrical shock. Always use insulated tools and wear appropriate personal protective equipment such as gloves and safety glasses. Remember, electricity is a powerful force that can be dangerous if not handled properly. By following the NEC guidelines on grounding and bonding, and by taking appropriate safety precautions, you can minimize the risk of electrical accidents and ensure the safety of people and property. In the realm of electrical safety, meticulous adherence to regulations and best practices is non-negotiable. The proper implementation of equipment grounding conductors in conjunction with EMT exemplifies this commitment to safety. While EMT provides a degree of physical protection to conductors, its role as a grounding path is limited and unreliable, hence the mandatory requirement for a separate equipment grounding conductor.